Wanted to make you this short video because it's unlikely that we can finish all these examples from section 5.5 in class. The last checkpoint was solving trigonometric equations using the appropriate method. And anytime you're learning to do something that has lots of different methods, as long as you're using one method at a time, it's pretty straightforward. Like when you're learning to factor, as long as you're factoring difference of two squares, you know exactly what to do. That's easy. When you learn to factor the perfect square trinomial, if you do a dozen of those in a row, it's easy. But what gets difficult is when all the different kinds are mixed together and you have to decide what to do. The same is true of solving equations and solving trigonometric equations. The previous objectives, we were using one tool at a time. And here in the mixed practice exercises, we've got to figure out what method to use on each problem. Our instructions are to solve each equation on the interval from 0 to 2 pi. And if exact solutions are not possible, express the solution correct to 4 decimal places. Those are the problems where we will have to use an inverse trig function to get a decimal approximation. The rest of them you can find exact answers. So number 8. Two first things I notice about number 8 are that because it's first degree, I can treat this like a linear equation. I can treat that sine of 3x as some ugly, and I don't actually have to rewrite the problem with u in the place of sine 3x. I'm just keeping in my mind that that's the first thing I need to do, oscillate that ugly or that sine of 3x. So I'm going to subtract square root of 3 from both sides, divide both sides by 2, and I'll have sine of 3x equals negative square root of 3 over 2. Now, I said there were two things I noticed as soon as I looked at that equation. The first one was that it's like a linear equation. The second one is that because this x has a coefficient other than 1, remember that's a period change on that function. The period of this function, make a note out here, the period of this function, instead of being 2 pi, would be 2 pi divided by 3. And so whatever this function would normally just do twice in one revolution of the unit circle, it's going to do 6 times. We're going to have 6 solutions here. So the first thing I'm going to have to think is, where is sine negative square root of 3 over 2? Sine is negative in the 3rd and 4th quadrants, and it's almost negative 1 by the y-axis. So I'm looking for this angle and this angle being 6,676,86 or 4/3 pi, and this angle being 9,610,6 or 5/3 pi. So if this was just sine of x is negative square root of 3 over 2, and I was looking for answers in one revolution of the unit circle, I would have only these 2 solutions. But because of the period change, I need to set my 3x equal to 4/3 pi and all of its coterminal angles, or 5/3 pi. Oh, I forgot what I was doing for a second. 3x equals 5/3 pi and all of its coterminal angles. Now, if these instructions had said find all solutions, then again, we would be through right here. We have the 2 times I just realized that's not true. Let me take one more step and then I'll finish that sentence. Divide both sides by 3. Make sure you're dividing both terms by 3. You'd have x equals 4/9 pi plus 2/3 pi n, and x equals 5/9 pi plus 2/3 pi n. Now, what I started to say was, if this said, find all the solutions in infinitely many revolutions of the unit circle, then we would have all the solutions by letting n be 0, then letting n be 1, then letting n be 2, etc. But because we're only looking for solutions in the interval from 0 to 2 pi, including 0, but not the 2 pi, I need to find for what values of n these angles are within that interval, 0 to 2 pi. So I'm going to let n be 0 and see what solution that gives me, and then let n be 1 and see what that solution gives me. And I'm going to keep doing that until I'm outside the bounds of 0 to 2 pi. If n is 0, then I'd have the solution 4/9 pi. If n is 1, I'd have 4/9 plus 6/9 is 10/9 pi. And if n is 2, then I would have 4/9 plus, let's see, that'd be 4/3 or 12/9. 4/9 and 12/9 is 16/9. Now, that's almost to 2 pi. 18/9 would be 2 pi. So if I let n be 3, I would be outside that interval from 0 to 2 pi. These are the only 3 solutions I'm going to get from this equation. And I'm going to do the same thing with my other equation. When I let n be 0, I would just get 5/9 pi. When I let n be 1, I'd have 5/9 plus 6/9 is 11/9. Right? And when I let n be 2, that would be 5/9 plus 12/9 is 17/9. And that's the 3 solutions I get from this equation. Again, if I went to n equals 3, I would be outside the bounds of 0 to 2 pi. I was expecting 6 answers because of this period change, and that's exactly what I got. All right, on number 9. The first thing I notice about that is these 2 trig functions don't have the same argument. If there was some kind of Pythagorean identity that involved sine and cosine, not sine square and cosine square, I still couldn't use it here because these 2 expressions don't have the same argument. So I look up at the double angle, half angle, addition, subtraction formulas that I have, and I recognize that sine of 2x is one of my double angle formulas. In the place of sine of 2x, I can put 2 sine x, cosine x, and then I have the second term plus cosine x equals 0. I needed to do something about that argument being 2x. I didn't know in advance what would happen if I used the double angle formula. I just couldn't think of anything else to do. So I used the double angle formula, look at this equation, and then I happen to notice I can factor out a cosine x. If I factor out a cosine x, I'll be left with 2 sine x plus 1. And now each factor only has 1 trig function in it. I have 2 things multiplied together to give me 0. So either the first one equals 0 or the second one equals 0. And those 2 equations are pretty easy to solve. I know that the 2 times cosine of 0 in 1 revolution of the unit circle are pi over 2 and 3/2 pi. Those are on the y-axis where cosine is 0. And the other equation is like a linear equation. I would just subtract 1 and divide both sides by 2. And then think about where sine is -1/2. Sine is negative in the third and fourth quadrants, and it's -1/2 close to the x-axis. So the two answers we're looking for are about right here and right here. The first one is 6676 pi. And the second one is 869610.611 pi. And so that equation had 4 solutions. Right. Number 10, tangent x is -6.2154. That's certainly not a value that I can get from dividing any y coordinate by x coordinate that I have memorized on the unit circle. That tells me I'm going to have to use my calculator, and I'm going to have to use inverse tangent to undo this tangent. So I could take inverse tangent of both sides. On the left-hand side, that would just leave me x. And on the right-hand side, I'd have inverse tangent of -6.2154. Now, just to make this a little bit faster, I have entered that on my calculator already, and I got -1.4113. Now, think about this. This inverse tangent of -6.2154, that's the angle whose tangent is about -6. You think about the two quadrants where tangent has a negative value, that would be quadrant 2 and quadrant 4. And so I don't know exactly how many degrees or radians it is, but oops, that angle in the wrong place. Quadrant 2 and quadrant 4. Remember, inverse tangent is always going to give you an answer between -pi/2 and +pi/2. And that's what that -1.4113 is. It's how many radians this angle is below the positive x-axis. Now, I can't give that for one of my solutions because the directions say express all answers between 0 and 2 pi. So I'm going to think about the reference angle. If theta is -1.4113 is in quadrant 4, then the reference angle for that would be +1.4113. That's the symbol for reference angle, is +1.4113. But the two answers that I want to give are this second quadrant angle where tangent is negative, and this angle, but written as a number between 0 and 2 pi. To get this second quadrant angle, if the reference angle is about 1.4 radians above the positive x-axis, then this angle I'm looking for in the second quadrant is about 1.4 radians above the negative x-axis. So I can find that angle by just subtracting the 1.4113 from pi. And for that, I got about 1.7303. And then there's also a fourth quadrant solution. I just can't write it as negative 1.4. I need to write it as 2 pi minus 1.4113. And that's about 4.8719. That's a number between 0 and 2 pi. 2 pi is about 6.28. So both of those are between 0 and 6.28-ish. All right, number 11. First thing I think is that looks like a quadratic equation. So I try to solve it like a quadratic equation. I would isolate the secant square by adding 10 and dividing both sides by 5. I get secant square is 2. Now, if I wanted to keep working with secant, I could say secant square is 2 and think about where secant is 2 in one revolution of the unit circle. I think my brain would like that better if it were in terms of cosine. I could see it better. So I'm going to say if secant square is 2, then cosine square is the reciprocal of 2. Cosine square is a half. That's easier for me to think about because the cosine's just the x coordinate of on the unit circle. Now, I need to take the square root of both sides. And when I take the square root of both sides, I forget my plus or minus. So I have cosine x is plus or minus square root of a half. And I know I can write that square root of a half as 1 over square root of 2. Or when I rationalize it, that's square root of 2 over 2. How many times in one revolution of the unit circle is cosine either positive or negative square root of 2 over 2? Well, 4 times. It happens once in each quadrant at the quarter pies. So your solutions would be 1/4 pi, not 2/4 pi, because that's the y-axis, 3/4 pi, not 4/4 pi, that's a whole pi, 5/4 pi, skip 6/4 pi, and go to 7/4 pies. That's the quarter pies in each of the 4 quadrants. Cosine is either positive or negative square root of 2 over 2. Right, one more. I'm thinking number 12 also looks like a quadratic function or a quadratic equation, and I'd like to factor it. I could either think of tangent as being some ugly and tangent squared being some ugly squared. I could think of this as being like 3 ugly squared minus ugly minus 2 equals 0. And if I can solve this equation with uglies in it, I can solve this equation with tangents in it. I'd like to not have to do formal substitution. If possible, formal substitution is when you actually put the u in place of whatever it represents. I'm just going to think of this as being like that and try to factor it without using formal substitution. I know that 3 tangent squared pretty much has to be 3 tangent x times tangent x. And I know that the 2 either has to be 1 times 2 or 2 times 1. I'm good enough at foiling to see that in order to get a middle term of -1 tangent, I'm going to have the 1 here and the 2 there. And to get a negative tangent, I want the outer terms to be negative. I want the 3 tangent to be negative and the 2 tangent to be positive. And then I never, ever, ever go any further until I check my factoring. Sure enough, that gives me 3 tangent squared minus 3 tangent plus 2 tangent. That's negative 1 tangent. And then positive 2 times negative 1 is negative 2. So I'm sure that I have factored that correctly. I'm going to set each factor equal to 0. Actually, that one I went ahead and added 1 to both sides. I didn't mean to do that, but I did. This equation, the first equation, I'm going to subtract 2 from both sides and divide both sides by 3. And so my 2 equations are tangent x is negative 2/3 and tangent x is 1. Well, this one's easier to solve, the second one, because I know where tangent's 1. To get a 1, it has to be something divided by itself. And tangent is the y divided by the x. So where are your y's and x's the same? Well, that happens at the quarter pies. Specifically, tangent is positive 1 at 1/4 pi in the first quadrant and 5/4 pi in the third quadrant, where you have a negative divided by a negative. So this is 2 of the solutions that I get from tangent x equals 1. Now, I don't have an angle memorized on the unit circle where my y is 2 and my x is 3 and one of them's negative. That means I can't find an exact solution for that. I'm going to have to use inverse tangent. So x would be inverse tangent of negative 2/3. And I've already entered that on my calculator and gotten approximately negative 0.5880. Now this problem just happens to be a lot like number 10, because in number 10, we were looking for an angle whose tangent is negative, and we said tangent is negative in the second quadrant and in the fourth quadrant. So that's still the case here. This negative 0.5880 is the fourth quadrant angle where tangent is negative, but I can't write it in that form because it's not a number between 0 and 2 pi. Here's what I'm thinking. The fourth quadrant angle, negative 0.5880, means the reference angle is positive 0.5880. This terminal side of this angle is the same distance from the x-axis as this angle. And then there's a fourth quadrant angle, same distance from the negative x-axis as this is from the positive x-axis. So I'm going to find my second quadrant angle by subtracting that 0.5880 from pi radians. Quadrant 2 angle would be pi minus 0.5880, which I got to be 2.5536. And then I just need another name for this fourth quadrant angle. I need it written as a number between 0 and 2 pi. So I could say 2 pi minus 0.5880. And for that, I got 5.6952. Now, both of those are numbers between 0 and about 6.28. So I hope seeing these few more examples help you. I think this is a difficult concept on test 4, solving trigonometric equations. So you want to solve as many as you possibly can. Get a lot of practice. And if you need any help, just let me know. I'll be happy to help you some more.